Okay, so I'm going to try this again. I already recorded half of this lecture, but my computer did an update yesterday and deactivated the audio recording, so there was no sound with it. So I'm starting from scratch, and so I'm going to have to make sure I say all of the wonderful, insightful things I said the first time I recorded it. Okay, so today's lecture is the continuation of statics. Now, if you remember, statics, we wanted our object not to go up and down, side to side, and in and out of the page. But there's more to it. What happens if this thing wants to tip over? It's not sinking down into the center of the earth, it's not moving side to side, and it's not moving in and out of the page or in and out of the screen. It's tipping over. What if it tips over that way? What if, so that was that. What if it spins like this? So it looks like there's more to this keeping it still thing. So we're going to talk about moments and moment couples. We're going to talk about degrees of freedom, and then we're going to talk about free body diagrams. And free body diagrams are basically just very simple drawings that talk about everything that's happening on an object. It allows us to simplify and draw a diagram so that then we can use math to solve for reactions. And remember, reactions are all of the things that stop our object from moving. So let's jump in. Okay, so just some terminology to help us understand what we're talking about here. Okay, the centroid. The center of mass, the center of gravity, or the center of inertia. It's the mean position of matter in a body. It's the point about which a body will rotate if spinning freely, the intersection of neutral axes or median lines. Now, for a ball, that's going to be the center of the object. And it doesn't matter which way you spin that thing, the center of the object, the neutral axis, will always pass through it. For a person, you know that your center of mass is not at the midpoint of your height because you're heavier at the top. So your center of mass is kind of somewhere in your upper third or somewhere like that. So you're not, it's not in the middle of your height. You don't know exactly where, but you often hear people talk about it. How if you're skiing or skating, you want to get your center of mass down low to the ground. Well, why do you think that is? If you're standing up, it's a lot easier to tip over than if you scrunch down. And there's something to that. So we're going to get to what that is in a little bit. Okay. So if the centroid is the intersection of the neutral axes or median lines, what's the neutral axis? So we'll often draw a centroid like this. So sometimes we don't even draw the object, but this is the centroid. So if we have this object, this is its center of mass. Well, if I held a string like this, we know, like a mobile, that would try to spin. If we had a center of mass over here, it would try to spin, it would balance. You know how if you find a spoon, if you take a spoon, you can find a perfect spot to make it balance? Okay, so it's going to try to, that string should be over here. There's something funny with that diagram. The center of mass should be over here. That shouldn't have moved. So I'm going to fix that image here. So you'll see what I mean. We were talking about it being offset. I clearly moved the diagram and the centroid came with it. Slide 3. Okay. Okay, what happens if you push on an object through its center of mass? What do you think is going to happen? It's going to just slide along. Okay, so a force applied concentrically to a body will move or translate in line with the applied force. So put a force on an object, it tries to slide, like that. If you wanted to stop it, you'd have to put a force in the opposite direction, and then it wouldn't move. You would need an equal and opposite reaction to stop it from moving. What happens if you put a moment on an object or you try to spin an object? and you apply it around the center of gravity. So when a moment is applied to a body, it will rotate about its center of gravity. So you apply a moment, the object tries to spin. Okay, what happens if instead of applying a force through the centroid, you apply it offset from the centroid? So I apply an object not in line. Does this object still try to slide? Yeah, there's nothing stopping it from sliding. But do you think it does anything else while you're doing that? Does it also try to spin, possibly? So when you apply a force eccentrically to a body, it will both translate and rotate. So that object is sliding and it's spinning. So if a force was applied through the centroid, it slid, and a moment applied about the centroid called it to spin, but a force applied eccentrically causes it to slide and spin, that looks like we should be able to add some things up there. So the effect on the body will be the same as if a concentric force and a moment are applied to the body simultaneously. So a force through the centroid and a moment about the centroid is the same as a force eccentric from the centroid. So a force eccentric from the centroid caused it to slide and spin. A force through the centroid will cause it to slide, and a moment about the centroid will cause it to spin. So these two things were the same as the force eccentric from the centroid. We call that spinning a moment. And if we wanted to try to quantify that, and we know that it had something to do with a force eccentric from a centroid, we know moment causes a body to rotate. If you apply a force eccentric from a body's center of mass, it will cause it to rotate. The farther away the force is from the centroid, the more it wants to rotate. Or the larger the force, the more it wants to rotate. So there's some combination of the amount of force and its distance from the centroid. The distance is E, or the moment arm, or the eccentricity, depending on the context. And so we have a distance that impacts the moment, and the value of that force impacts the moment. So the force is F, and it looks like a combination of E and F could equal our moment here. Moment M is the equivalent of the force times the eccentricity. So this force with a moment is the same thing as a force with eccentricity. Both of these two things will cause it to slide and spin. So eccentric force equals force and moment. So this is equivalent to this, where M is P times E. An eccentric force is equivalent to a force through the centroid plus a moment about the centroid. So it seems like if we're talking about forces and we want to relate them to moment, there has to be an eccentricity involved. Let's talk about values for these things. We have 25 kilonewtons acting half a meter away from the centroid. Okay, well, we've been told that the value of that moment is the force times the eccentricity. So 25 times 0.5 is 12.5. We still have our force acting through the centroid, but this is the equivalent of 12.5 kilonewtons through the centroid and, 25 kilonewtons through the centroid and 12.5 kilonewton meters causing it to spin. These two systems are equivalent. Both of them are going to try to push downwards with 25 kilonewtons of force, and both of them are going to spin with 12.5 kilonewton meters worth of moment. Well, what if we only wanted to duplicate the rotation, but not the sliding? What if we wanted to stop that thing from sliding? We only wanted to talk about rotation. So we want rotation, but not translation. We need something to stop it from sliding, like an equivalent force in the opposite direction. Remember, when we had a force pushing this way, to stop the object from sliding, we needed an equal and opposite force pushing in the other direction. So, if we had a moment causing this to spin, but it's not sliding, take a look at this. This force is trying to push it this way, and this force is trying to push it this way. They're going to stop each other. This force is causing it to spin in this direction, and this force is causing it to spin in this direction. So both forces are causing it to spin in that direction, but they're stopping the object from sliding. This is an equivalent force couple. So these two forces, these equal and opposite forces, are the same as just a moment causing our object to spin. Okay, so both of these things are just spinning and not sliding. Okay, what happens if we have a force causing our object to spin because it's some distance away from the centroid, and some force causing it to spin some distance away from the centroid? We should be able to see what's happening here. Well, this force is causing it to go down, and that force is causing it to go up. So it looks like they're going to cancel each other out. They're equal and opposite. So the object's not going to slide. It's static from going up and down. This arrow's causing our object to spin like this, and P2's arrow is causing the object to spin like this. So we have our first moment, and we know moment is force times eccentricity. So 12.5 times 0.5. So 12.5 times 0.5 is 6.25. And we have 12.5 times 0.5, or 6.25. And we'll add them up, and both of them are causing this object to spin with 12.5 kilonewton meters of moment. So these two systems are equivalent now. There is nothing causing it to go up and down because one's pushing down and one's pushing up, and they're canceling each other out, but they're both causing it to spin. So these two systems are equivalent. They're both trying to spin and nothing else. Don't worry, you're gonna get good at doing this. Don't worry too much about it. I know I'm saying a lot of numbers and words. These are so you can go back and look at them whenever you start to get a little fuzzy on it, but we're gonna start doing lots of these very quickly. Okay, moment, like force, is a vector, but it's an awkward one to kind of draw. We don't like drawing it very often, so we have some tricks that we do. So moment can be represented as a vector. What we often do to differentiate moment as an arrow is we'll put two arrowheads on it. It's just kind of a lazy way of us saying we're talking about moment. So the magnitude of the vector would be force times eccentricity, and the direction of the vector is parallel to the axes of rotation. So what we're saying is this is the axes that the moment is trying to spin about. So it's trying to, it's funny for me, it's trying to spin that way. All right, so if that's our axes, it's trying to spin about that axis. Okay, so that is what the direction of the vector is. We find it a pain in the butt to draw a moment as a vector often, but it's handy to understand why we talk about it as a vector, because there's a trick to understanding what direction it's spinning. Okay, so what we're saying is these two things are the same. This is our vector, it's a double-headed arrow, and it is force times eccentricity. And this is the axes we're spinning about. What we're saying is this moment is spinning about this axis. Moment vectors are added in the same way we could add other vectors. We're not going to do a lot with that, but it's good to know that the rules apply for it. We like to know that a vector or that moments can be represented as a vector because it helps us talk about what direction things are spinning, and it's going to help us keep track of what's positive and what's negative. So the direction of a moment vector can be determined from your right hand. It has to be your right hand. If you use your left hand, these rules don't work. It's your right hand. Okay, so if you hold your right hand and point your thumb in the direction of the moment vector, your fingers curl in the direction the object is spinning. Okay, so if we went back to that one that we showed on the last slide, so you can see that my thumb is pointing in the same direction as the vector, and my fingers are curling in the same direction that the moment is spinning. This right hand rule is going to be very helpful when we're talking about what direction a moment is, if it's positive or negative. And you'll see what I mean by that in a few minutes. Okay, so your thumb points in the direction of the moment vector, your fingers curl in the direction of the moment. If your thumb points in the positive direction, it's a positive moment. If it points in the negative direction, it's a negative moment. So remember, for the y-axis, upwards was positive. Point my thumb upwards, my fingers are curling in the positive direction. If my thumb is pointing downwards, which is negative, my fingers are curling in the negative direction. If my thumb is pointing in the positive direction for you guys, my fingers are curling in the positive direction. So we're going to start to do a bunch of these because it's going to be really handy when we talk about it when we're trying to solve our equations. Okay, thumb upward, we're spinning in that direction. Our fingers are curling in that direction. So really what we're saying is there are 6 degrees. By the way, it's St. Patrick's Day, so I'm wearing St. Patrick's Day shirts. Our whole family is. So there are 6 ways a body can move. If you want to talk about it, you can sum these up so it can really move in any direction. But if we're talking about our principal axes, an object can move up or down, side to side, or in and out of the page. The object can also spin about any of these. It can spin about the y-axis, it can spin about the x-axis, and it can spin about the z-axis. So, translation parallel to x, translation parallel to y, translation parallel to z. Rotation about x, rotation about y, rotation about z. We find it very hard to do or keep track of math for 6 degrees of freedom or a 3-dimensional world. We often simplify into a 2D drawing, understanding that there are 3 2D drawings happening simultaneously. This one, and this one. So you could hold your piece of paper flat on an XZ plane. You could hold your paper like this on a YX plane, or you could hold your paper like this on a YZ plane. We often, because we're talking about our paper and you're seeing it like this, we often work in an XY plane, okay? We know that there's still a Z axis out there. So what we're saying is we're going to forget about movement in and out of the page. We're going to forget about rotation about the y-axis, and we're going to forget about rotation about the x-axis. So we're saying that there is a restraint for translation in the z-axis, there is a restraint for rotation about the y-axis, and there is a restraint for rotation about the x-axis. So what we're left with is a 2D plane where we're talking about things moving up and down, side to side, and spinning about our z-axes, okay? So if outwards from the page is positive, you point your thumb outward from the page, your fingers are curling in that direction. So that's the positive direction for a moment about the z-axis. So a free body diagram. What is a free body diagram? A free body diagram is a simplified drawing that shows all the forces acting on a body through the center of mass where applicable, all the moments acting on the body, all the restraints that keep it in equilibrium, and all the dimensions from a reference point to those forces, moments, or reactions. And so this is a great visual technique to help us understand what's happening to our object. So let's take a look at a free body diagram. So if this was a car, for example, we know that there's some weight pushing down on the car, and there are reactions pushing up from the bottom of the ground. So there is something stopping this car from sinking down into the center of the earth. And that is going to be where the car tires sit on the ground. I've drawn this in 2D. You understand that there is a third dimension. There is in and out of the page. That this car has a third dimension. And in fact, that these front tires represent 2 tires, and this rear tire represents 2 tires. So we will often simplify things into 2D. It's our job to remember that there's other things happening there. So look at this. We've got the weight, which is the force acting on it. We've got our reactions. That's great. And we've got dimensions from some reference point. They've picked this point right here. So we know how far away our F is from that point. We know how far away our R is from that point. And we know how far away our weight is from that point. They haven't given us this dimension, how far our weight is from the x-axis. I'm going to add that in. Because that should be in there too, because it's not on the x-axis. So that could be valuable information as well. So again, it's just a very simplified drawing. We could have even represented this car as a line if we wanted. So we want this to be as simple a drawing as possible, using arrows or vectors to represent our forces and our moments. Okay? It can get more complicated than that. So look at this. Now, this is more complicated than what I'm going to make you solve. We are going to be doing a lot of free body diagrams. And if you were doing a physics class, this would be a classic one. In fact, this one is so ubiquitous in a physics, in your first week of physics class. We've got our weight pushing down into the center of the earth, but it isn't normal to ground. We have the force stopping it from sinking into the center of the earth, and we have friction stopping the car from sliding down the hill. We're assuming the parking brake is on, and this is not trying to roll. That is a different part of physics. That would be dynamic action. We are talking about when it's stopped, and we don't want, assuming these cars are locked in place, these tires are locked in place and the brakes are on, the emergency brake, everything, we still don't want this to get so steep that it slides down the hill. Some of you must have done physics. I remember the funnest physics question ever was a bowling ball, and you've thrown it with a force and a moment, and for some portion of it, it slides until friction takes over, and then it rolls, and you had to calculate how far it got down the bowling lane in a certain amount of time. And that was one of my absolute favorite physics questions. Can I remember how to do it? No friggin' way. But at one point, I was smart enough to know that level of physics, and probably a good chunk of you did some of that as well. We don't care about it moving. We want it to be still. If it's rolling, nope, done, not our problem. If it is sliding, something's failed. We now don't have a static object. We want our objects to be stationary, and we want to know what it takes to ensure these are stationary. If we found out that there was a certain reaction required here to keep this in place, well, then we could figure out if there was enough friction for that. And if there wasn't, we would know this would roll down the hill or slide down the hill. So our job is to figure out what does it take to not move, and then ensure that that thing is there to make sure it doesn't actually move. So how do we draw free body diagrams? Well, we know our coordinates where y is up, or y is up and down, and upwards is positive. X is back and forth, and we know to the right is positive. We know Z is in and out of the page, and out of the page is positive. A force we can draw as a vector. A moment or torsion we can draw as a vector. Uniformly distributed load or a stress profile. These are all the same way of drawing the same thing. Basically what we're saying is that every little section of that object has some load acting on it. So instead of one point load standing right in the middle of our object, we've taken that load and spread it evenly all out over the object. We're going to talk a lot about uniformly distributed loads later in the term, and we're getting pretty close to the end of the term, so you know that that's not far away. So if you see something that looks like this little triangle is saying that we have a pinned support. A pinned support is saying that our object in that spot can't move up and down or back and forth, but it can rotate about that spot. That doesn't mean the whole object is rotating, but it can rotate about that spot. How could a whole object not rotate, but it be allowed to rotate about a certain spot? Okay, well, we've got our beam here. This object is not spinning in space. It's deformed some, but look at this. It's rotated about the ends. So I am creating a pinned support at the ends. If I was creating a moment connection at the ends, I wouldn't let it rotate. A roller support only stops it in one direction and allows it to roll in the other. You can have a roller support that stops movement in the y direction. You can have a roller that stops movement in the x direction. Obviously, you can also have a roller that stops movement in the z direction, but we're focusing on our 2D plane. A fixed or moment connected support does three things. It stops movement up and down, side to side, and about our z axes. Okay, so this is stopping movement up and down, side to side, and it's preventing rotation about the z axes. I'm going to turn that to be in the positive direction. All right, how do we draw these symbols? So this is really annoying, I think, for some people. A pin is a triangle that looks like this. A moment connection is on the object itself, and we draw a solid filled-in triangle. What we're saying is those two objects are fused together in some way. They can't rotate relative to each other at that spot. So if this was a column and this is a beam, this beam is fused to this column at that spot. We have to maintain always a 90-degree angle between those two things. A pinned connection, this column is going to support this beam, so it's going to stop it from going up and down. It may or may not stop it from going side to side, but it won't stop it from rotating. So this object can rotate about that column, or just like this, okay? What does statically determinate mean? Statically determinate means there's at least one restraint for each degree of freedom. So there is a force reaction in the x direction, there is a force reaction in the y direction, And there is something that stops it from rotating. So that means there's either a moment reaction, or what did we say a moment could be represented as? That's right, a force couple. So the thing that stops it from rotating in space could be a moment reaction or a force couple, because we know a moment and a force couple can be equivalent. So remember, a force couple was two equal and opposite forces causing the object to spin in the same direction. Let's take a look at some free body diagrams. So this is a beam with a pin support here and a roller here, and it's showing a uniformly distributed load. So you remember way back when we were talking about loads and we had a factored dead and live load combination and we called it UDL. I apologize, but we're using UDL again for something else now. We are very lazy and there's only so many letters in the alphabet, but unfortunately, uniformly distributed load we'll often abbreviate as UDL. It'll be pretty clear from the context what I'm talking about. I will often usually try to type out uniformly distributed load instead of abbreviating it with UDL. So we have this beam that's supported at two ends. One end can move back and forth a little bit and the other one can't. And there are no moment connections anywhere. The free body diagram of this object, we know a pin stops things from going up and down and sliding back and forth. So we can represent this as two arrows that would be the reaction. So here's the arrow that's stopping it from going down into the center of the earth, and here's the arrow that stops it from sliding back and forth. Our roller support, we know a roller, we were told, only stops things from going up and down. So we can represent that with this reaction arrow as well. So this would be the free body diagram of this object. So let's take a look at some other free body diagrams. This is the one we just looked at. We have a pinned roller support condition. Here's a cantilever. Well, look at this. They've drawn this as a moment connection. We know a moment connection stops things from sliding back and forth, moving up and down, and it provides moment restraint. So we would draw the free body diagram to look like this. This one, I can tell you, is a wonky condition. It's not something we would do very often, and we need this to not move up and down, slide back and forth, or spin in space. So let's take a look. What do we have here? This looks like a roller in this direction, but a pin in this direction. So it stops it from sliding up and down. This end, it's stopped from moving back and forth like this, but it can slide up and down. And then this is a moment connection. So it stops it from spinning. So up and down, back and forth, rotation. So we've restrained all 3 degrees of freedom on this. Now you're looking at this one and you're saying, we've stopped it from going up and down, and we've stopped it from going back and forth. We haven't stopped it from spinning in space. But look at these 2 arrows. We have 2 arrows some distance apart. We don't know the value of these. We're just drawing these as placeholders. If this tried to spin in this direction, this arrow could very well be holding it down. We don't know, but it looks like we could make an argument that something is stopping this from spinning in space because we have reactions some distance apart. So what is a roller? Can we actually detail a roller? I'm going to tell you that in steel construction, roller conditions and a moment released condition just tend to happen. So what makes sure that that roller connection doesn't have a moment reaction there? Well, the way we detail things for normal objects, this connection here, and this is a typical connection for a beam into a column. Okay, so this is, my hand is my column, this is my beam, and when our object bends, it allows rotation at that joint. And this is how we often end up having rotation at that joint. How do we release the load in the X direction? So what makes it a roller, not just something that doesn't stop rotation? Well, columns often skew just a tiny little bit, not much. Like we're talking, if this moves 0.001 millimeters in either direction, it has released it. It is a roller in that direction. I don't want you guys to fuss too much about this. I just want you to understand that normal detailing of a beam, so if we're talking about the normal world, the normal way we detail things, which means the way we build it or draw or dictate the way it gets built, we often have, for a regular old normal beam, a pin roller condition. So one end is stopped from going up and down and back and forth, and the other end is stopped from going up and down. This is just to give you some context on how that actually is detailed. If we have a very, 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 very large structure and we want that, we don't want to restrain it for rotation, we actually have to do special things to make sure that doesn't happen. So here's an image of an actual roller connection that would allow rolling there. For large bridges, for sliding in the X direction, we actually build our bridges so that one end is on a Teflon pad. So if you're driving down the highway the next time and you look at an overpass, those big concrete overpasses, you will see that there's a ledge and one end of that sits on a pad, and that pad is actually a Teflon connection, and it's allowed to slip relative to each other. Okay, so equilibrium. We talked last week about, in equilibrium, the sum of all of the forces up and down have to be 0, and the sum of all of the forces sliding back and forth have to be 0, so that it's static. We said it's not moving. Well, to be static, it also can't be spinning in space. So our object as a whole, we can have rotation about one end, but we don't want the object to be flying off in space or spinning in space. So it's not moving and it's not rotating, the object as a whole. So we want to figure out, for an object like a building that has loads applied to it, what do we need to make sure it doesn't move up and down or spin in space? Once we figure that out, we can design whatever we need to make sure that doesn't happen. So this beam, for example, with a load on it, so we've got the calculator load on it, wants to slide down into the center of the universe, or the Earth. But I am going to have columns at the end that's going to stop that from happening. If I know how much this calculator is pushing down on my beam, I can figure out what load my columns need to resist. And if I do that by assuming my columns are the reactions at the end, I can figure out then how I design my columns. So we figure out the load on the beam, design the beam. Then we figure out what that does to the columns, and then we design the columns. Then we figure out what the columns do to the foundation, and we design the foundation. And then we figure out what the soil does as part of that foundation design as well. So is our foundation good enough to transfer that load into the soil without the soil failing? So what we do is we figure out the loads, and then we chase it down through the building, making sure every element within it is stable, strong enough, and stiff enough. Stable is really that exercise of drawing our free body diagram. That is us actually doing a diagram that shows stability. If this object can slide up and down, back and forth, or spin or rotate as an object, it is not in equilibrium, therefore it is not static, which means we do not have a stable object. Now, we live in a world with things that aren't stable, and we use that to our advantage. A ball being thrown in the air is not stable. It doesn't mean it doesn't work. It does what it's intended to do, But we care about our buildings not doing that. We don't want our buildings to do that. So that is why what we're going to do is talk about things being static. So if it's static, we're saying the sum of all of the forces up and down. We're going to talk about it in a 2D world. The sum of all of our forces going up and down have to be zero. So if there's a load on it, we need a reaction that stops it from going downwards. If we have an object that has a force on it that's trying to make it slide, we need a reaction that stops it from sliding. If we have a force on our object or a moment on our object that's causing it to spin, we need something that stops our object from spinning. So we need to figure out what these reactions are to make our object stable and safe. So a body in equilibrium may not rotate or translate in all degrees of freedom. To remain in equilibrium, there must be an equal and opposite force or moment to keep it in place. These are called the reactions. Or, the sum of the forces and reactions in each direction must equal zero. If we're talking about a system with 3 degrees of freedom or 3 degrees of possible movement, we need to prove it's not moving in these 3 directions. So we are going to have 3 handy directions. The sum of all of the forces in the y direction have to be zero. The sum of all the forces in the x direction have to be zero. And the sum of all of the moments about our z-axes have to be zero for our object to be in equilibrium, for it to be static, for it to be stable. That's what we want. So, sum of the forces in the y have to be zero, the sum of the forces in the x have to be zero, and the sum of the moments about the z-axes have to be zero. These little arrows are just a handy reminder that upwards is positive for y, to the right is positive for x, and spinning about a vector about the axes with the vector coming out of the page using our right hand rule is positive for z. So these are just reminders of what's positive. This just means the sum. This is telling us what direction we're talking about, and we want all of them to be zero, okay? Otherwise, it's not static, and that is the definition of what we need. We need this to be static. So let's start doing some examples. Okay, I'm going to take a quick break and fill up my water. Okay, so let's take a look at this example. We have a teeter-totter. So somebody complained last year that it was ridiculous that I used a teeter-totter because everyone knows how a teeter-totter works. But then they also complained, why would there be math in this course? Nobody knows math. The reason I picked the teeter-totter is because you intuitively understand how a teeter-totter works. Most of you have been on them, so you understand what's happening with a teeter-totter. And we use this one because it allows us to use the math or do the math and draw the free body diagram of an object we already understand how it's moving. And if we can do it on one we understand easily, that means we can use that information and try to apply it to the slightly more difficult ones. Okay? So a teeter-totter, we know this teeter-totter is not sinking down into the center of the earth. That's not what it's doing. There is this pin holding it up. This is where I say you understand that a pin stops things from moving up and down and back and forth. But you know that this does not stop it from spinning about this point. Okay, so you understand a pin reaction. You know that this stops it from going up and down, and the teeter-totter's not moving back and forth in this direction, but you know that it could spin about this point. And that is what we want to formalize, and we want to formalize this mathematically. Okay, we're going to look at an example on a teeter-totter with 2 Shannons. 2 of me. I know the world has been blessed with 2 Shannons, and both Shannons are sitting the same distance apart from the center of the teeter-totter. I was an only child and didn't have many friends. I would build a teeter-totter with a piece of lumber and a seesaw horse in my backyard, and I would find a rock and try to position it in a spot to represent the second Shannon. Now, some of you already can see where this is going. Was the rock the same weight as me? Probably not. So you know intuitively that there's some funky stuff that can happen there with the teeter-totter. But let's start with this one where we have two Shannons the same distance apart from the center of the teeter-totter, or the support of the teeter-totter. The first thing we want to do is draw the free body diagram of this. So this is two Shannons. All right, so we've got two Shannons in this example. We have our teeter-totter. We know that there is a reaction here that stops this teeter-totter from going up and down and back and forth. So we know that there is some reaction in the y direction and some reaction in the x direction. We don't know what the values are. We just know that somebody drew something there, or that they built something there. We don't know what capacity it has or what value it has, but maybe we can figure out how strong it needs to be. We also know that there are two Shannons. Let's take a look here. They have told us how much Shannon weighs and where Shannon is sitting. I'm going to add that into the other slide. That was... Okay, so they have told us that Shannon weighs 0.65 kilonewtons. And Shannon is sitting 0.8 meters away. So we have P Shannon 1 and P Shannon 2. Let's draw this part in black. And we have E Shannon 1 and E Shannon 2. So we have a free body diagram drawn. We don't know if this is an equilibrium or not. And we need to know if it's an equilibrium. We need to know if this teeter-totter is static, because that's what we care about. We don't want our buildings to move. Now, intuitively, what do you think? Two Shannons that weigh the same amount sitting the same distance apart on the teeter-totter. Well, we have an arrow that stops it from going down into the center of the earth. We know that that pin there stopped it from sliding back and forth. But is this going to rotate about that point? Intuitively, what do you think? Two Shannons that weigh the same, sitting the same distance apart. I think you know intuitively it does not rotate here. So we were told that PS1 equals PS2 equals 0.65 kilonewtons, and ES1 equals ES2 equals 0.8 meters. Okay, we need to know if this thing is static. Okay, let's sum our forces in the x direction, where everything moving that way is positive, and we want to know what it takes for this system to be in static equilibrium, or for the sum of all of the forces in the x direction to be 0. So let's take a look at what we have. We have our x, and we don't have anything else moving in the x direction, do we? So Rx equals 0. Great. Rx is 0. Let's sum our forces. Let's find out what it takes for everything up and down to be 0, with upwards being positive. Okay, let's see what we have. We have PS1 acting downwards. Downwards is negative, so minus PS1. We have PS2 acting downwards. Downwards is negative. And we have R1 acting upwards. We didn't know that was upwards, but we've taken a guess that it's acting upwards, and upwards is positive. So plus Ry equals 0. Well, we know what the value of PS1 is, and we know what the value of PS2 is. So we have minus 0.65 minus 0.65 plus Ry equals 0. For this to be in static equilibrium, Ry has to equal 0.65 times 2. If we rearrange our equation, 1.3. So for this to be in static equilibrium, Ry has to equal 1.3. Let's sum our moments about the z-axis, where everything's spinning in that direction is positive. So remember, if I use my right hand and I point my thumb out of the page, my finger, which is positive, remember, out of the page and the z-axis is positive, so my fingers curling in that direction is positive. And so I've just drawn that arrow to show that. And we want to know what it takes for this system to be in equilibrium. The only problem is we don't have a moment reaction. Let's talk about spinning this object right here. We're going to talk about spinning it about our point R, or our reaction. There is no moment reaction there. We just have two things causing this to spin. Does Ry cause our object to spin about this point? No, it's passing right through the point that we're supporting it on. Does Rx, if we're spinning about this point, Rx doesn't cause it to spin, because to be a moment, you need a force and an eccentricity. But about this point right here, PS2 is causing it to spin in this direction, and PS1 is causing it to spin in this direction. Let's formalize that. So if we put a thumbtack right here, PS1 is some distance away from our centroid, and it tries to cause our object to spin in that direction. So if I curl my fingers in the direction it's trying to spin, and then point my thumb, that means it's spinning in the positive direction. So PS1 times, and remember, to be a moment, you need a force and an eccentricity. So PS1 times ES1, spinning in the positive direction, is trying to rotate this object. R1 doesn't cause it to, or Ry doesn't cause it to spin, Rx doesn't cause it to spin, but PS2 does. It pushes down right here, and it causes it to spin in this direction. I use my right hand, and I curl my fingers in the direction it's trying to spin. If I point my thumb is pointing into the page, which I know in the z-axis is negative. So minus PS2 times ES2. There is nothing else causing this to spin. We don't have a reaction causing it to spin. So the sum of all of that, we want to see if it equals 0. Well, PS1 we know is 0.65 times 0.8 minus 0.65 times 0.8 equals 0. Well, if we look at that, 0 equals 0. So it's in equilibrium. Okay? This one intuitively knew. What we did was formalize what we know. The thing we didn't know is how strong this support needed to be to stop the teeter-totter from sinking down into the center of the earth. We knew it wasn't moving this way, and we knew two equal and opposite forces the same distance apart from the centroid wasn't going to cause this object to spin. We've got a scale here, essentially. So let's take a look. What happens if we switch this up? Okay, so here's that worked out for you. So you can write it this way if you wanted. There's more than one way to write this out. So here I've written it out where I've taken that force with an eccentricity and rewritten it as a force through the centroid and a moment. So this PS1 and this MS1 is the same thing as our PS1 with an eccentricity. So you can write it in this way if this helps you. What happens if Shannon gets off the teeter-totter and Dave gets on the teeter-totter? So now, instead of two Shannons, there's Shannon and Dave on the teeter-totter. And let's face it, Dave weighs a lot more than me, but he sits in the exact same spot Shannon 2 had been sitting. Intuitively, what do you think happens? I think you know intuitively that this side of the teeter-totter moves down to the ground, meaning it is not in static equilibrium, which means in our world, this thing does not work. Let's formalize it mathematically. So they're going to tell us how much Dave weighs. So Shannon hasn't changed, and Shannon's sitting in the same spot she was. But instead of Shannon 2, we've got Dave sitting in the same spot. So the distance or the eccentricity is the same, but the weight is different now. So let's formalize this. So I'm going to do it without converting it to a moment first. You can choose to do it that way, and you'll see that it's worked out that way in the slides. So Shannon and Dave, same distance. Okay, we've got Shannon and Dave sitting that same distance away from the center of the teeter-totter. Okay, so here's our teeter-totter. Shannon is sitting here. Dave is sitting here. The eccentricity of Shannon and the eccentricity of Dave. We've been told, oh, look at that, the weight of Dave. We've been told that PS is still 0.65 kilonewtons. Dave weighs way more than Shannon. So sometimes he walks through as I'm giving these lectures. Weighs 0.85 kilonewtons, but the eccentricity of Shannon is 0.8 meters, and Dave kicked off Shannon 2 and sat in the exact same spot, so 0.8 meters. We know we have the teeter-totter support that stops this force from sinking in to the center of the earth, and it stops it from sliding back and forth. It does not provide a moment restraint at that location, meaning it can pivot about that point. We want to know if this thing is in equilibrium, or if it's not, what it takes. If there is something to stop it from moving, what does that take? All right, so let's formalize this. Let's take a look at the sum of the forces in the x direction and see what it takes for those to be zero. And let's just remind ourselves that everything in that direction is positive. Well, we have Rx and nothing else. So for this to be in equilibrium, Rx equals 0. That's fantastic. That's easy enough to do. Sum of the forces in the y direction, where everything upwards is positive. Well, we have Shannon acting downwards because downwards is negative. And we have the weight of Dave acting downwards, so that's negative. And we have some unknown reaction acting upwards. We don't know what its value is, but we know it's there. So maybe we could find out what it takes for this to actually be in equilibrium. So we have minus 0.65 minus 0.85 plus ry equals 0. We can rearrange this and see what it takes for this to be in equilibrium. So we have 0.65 plus 0.85. We need this teeter-totter to be able to support 1.5 kilonewtons. If this teeter-totter support can hold 1.5 kilonewtons, this thing can be in equilibrium. So that seems like it would be our job as designers to make sure whatever that is can support 1.5 kilonewtons. Now, we don't have anything to restrain it from rotating about that point. Let's see if it's in equilibrium. So we want to sum the moments about the z-axis, and we want to see if it's all in equilibrium or not. Let's pick this point right here, or where our reaction is, and let's just remind ourselves that everything spinning in that direction, or with a vector pointing out of the page, would be in the positive direction. Okay, we're putting our thumbtack right here. Our y passes right through the object, or right through the centroid, or through our pin, so it does not cause our teeter-totter to spin. Our x passes right through the spot we're talking about. It does not cause it to spin about that point. If we put our thumbtack right here, Shannon causes our teeter-totter to try to spin in that direction. So let's curl our fingers in the direction Shannon tries to cause the teeter-totter to spin. And so then I can point my thumb of my right hand, and that tells me, if my thumb is pointing outwards, that shows me that my vector is positive. So plus the moment Shannon causes the teeter-totter spinning about that point, which is PS times the eccentricity of Shannon. If our thumbtack is here, Dave causes our object to spin in that direction. So if I curl my fingers of my right hand in the direction Dave tries to make it spin, and then point my thumb, that tells me Dave's trying to spin it in the negative direction. So minus the force of Dave times the eccentricity of Dave. Remember, to be a moment, you need a force and an eccentricity. And then it doesn't look like there's anything else causing this to spin. We don't have a reaction that can restrain it from spinning. So there's nothing that we can use to try to say, hey, if this thing's strong enough, it won't spin. We only have the actual loads applied to it. Let's calculate this out. We have 0.65 times 0.8 minus 0.85 times 0.8. Let's calculate this. 0.65 times 0.8 minus 0.85 times 0.8 equals minus 0.16. That does not equal 0. This is not in equilibrium. This is actually trying to spin in the negative direction. Look at that. We've got something trying to spin in this direction. Dave is heavier than Shannon, so he's going to make the teeter-totter go down, which looks like it's spinning in the negative direction. So we've proven that this isn't in static equilibrium. So this teeter-totter is not in static equilibrium, which means as building designers, we don't like it. This thing isn't static. If it moves, it's not in our realm of the world. This is mechanical's problem now, more or less. I'm being a bit silly there, but you see what I mean. We can use these three equations to figure out what it takes to be in equilibrium, and if there's nothing to put it in equilibrium, is it in equilibrium on its own? If we had made this a moment connection, we would have known we would need a reaction that could withstand 0.16 kilonewton meters of moment. But it's a teeter-totter. It doesn't have moment restraint at that point. Okay, let's take a look here. Okay, so I have that worked out here. We have that it is not in equilibrium, and Dave makes the teeter-totter fall down until it hits the ground. Once it hits the ground, we have another reaction right here. It's a different system now. Now we have two reactions. We know it stops rotating, but there's no moment restraint. We have a reaction here in the y direction and a reaction here in the y direction. But all of a sudden it stops rotating. That's kind of interesting. We'll take a look at that when we look at beams in a little bit. What if I wanted to figure out what it took for this to be in equilibrium by Dave moving? Okay? Let's take a look at an adjusted Dave and Shannon. All right. So Dave is willing to move around on this teeter-totter to make sure the teeter-totter is in equilibrium. I'm lazy. I'm not going to move. I'm going to make Dave move, but I want this teeter-totter to be in equilibrium. So I've said, Dave, you have to move around to stop this thing from teetering. Which way do you think Dave needs to move? Does he need to move forward or does he need to move backward to stop this thing from rotating? Now, some of you are intuitively understanding that if moment is force times distance, the further away it is, the more it tries to spin. If Dave was causing it to spin more than Shannon, you need Dave to make it spin less. For Dave to make it spin less, his eccentricity needs to be less. Or intuitively, if you were two kids playing on the playground, you would intuitively know Dave needs to scooch forward a bit to stop it from spinning. You see kids do this all the time. They don't know that moment is force times eccentricity. They don't know how to sum all of the moments about the point of rotation to see if it's in static equilibrium, but they do intuitively know that one person needs to move to make this be in static equilibrium. And so this is where I say everything you need to know about structures you actually already know. I am just making it very complicated and formalizing it. Why do I do that? Because there are some problems that you can't look at and intuitively solve. So if we use the ones we intuitively know to come up with a mathematical process to solve it, when we get to the hard ones, we already have a process we can use to solve them. This one's simple. We're going to prove it with math so that we can take that process and apply it to the hard ones. Okay. So how far away does Dave need to be for this to actually be in static equilibrium? So Shannon, we still know weighs 0.65. Dave is still much heavier than her and weighs 0.85. Shannon is still sitting 0.8 meters away from the point of support, and we don't know where Dave's sitting. We need to figure out where Dave needs to be to stop this from spinning. We've talked about it. We think Dave needs to scooch forward a bit, or that this distance needs to be less than 0.8. We don't know what the exact value is. If we were out there on the teeter-totter, we'd kind of move around and figure it out. So let's formalize this. Let's do it mathematically. Okay. Dave and Shannon but Dave moves. So Dave's gonna move so that this is in static equilibrium. Okay? So we have the same teeter-totter. We know it's sitting on a support here that stops it from moving into the center of the earth, and that stops it from moving back and forth in the x direction. We also know that we have Shannon sitting here, and Shannon's eccentricity away, but we know that PS is 0.65 kilonewtons, and that the E of Shannon is 0.8 meters. We know Dave is sitting here. We know that P Dave is 0.85 kilonewtons. And we know Dave is sitting some distance away. But we don't know what Dave's eccentricity is. We want this thing to be in static equilibrium. So let's go through those same three equations we've been using. Sum the forces in the x direction, where everything in this direction is positive, and we want to know if this thing is in static equilibrium, or what it takes for this to be in static equilibrium. The only force or reaction in the x direction is Rx. So for this to be in static equilibrium, Rx needs to be 0. Fantastic. I think this thing can support 0 force. All right. Let's see what it takes for this to be in static equilibrium in the y-axis. And a reminder to ourselves that everything upwards is positive. Well, our y, our unknown reaction, we've drawn it pointing upwards. That seems like a good place to start. Our y is pushing upwards. PS, or Shannon, is pushing downwards. That's negative, so minus the force of Shannon. And Dave is pushing downwards, which is negative. And we want to know if this is in static equilibrium or what it takes to be in static equilibrium. Well, our y is a thing we don't know. We know that Shannon is 0.65 and the weight of Dave is 0.85 kilonewtons. We can figure out that if we want this to be in equilibrium, the reaction, or this needs to be able to support 0.65 plus 0.85, or 1.5 kilonewtons. So for this teeter-totter to be in equilibrium, we don't need to be able to resist any load back and forth. We need to be able to resist 1.5 kilonewtons downwards. And there's a third part to making sure this is in static equilibrium. We want to sum all the moments about the z-axis, and we want it to be in static equilibrium, so the sum of all of those needs to be 0, meaning it's not rotating. And everything in that direction is positive. So let's see. We've got our thumbtack right here. Our y doesn't cause it to spin. To be a moment, you need a force and an eccentricity. And if this is where a thumbtack is, our y isn't causing it to spin. Our x is passing through our thumbtack and isn't causing it to spin. The weight of Shannon is. If we push this like this, you can see it's trying to spin in that direction. Can curl my fingers in the of my right hand in the direction it's trying to spin, and then I point my thumb. My thumb is pointing out of the page, so that must mean Shannon's causing it to spin in the positive direction. To be a moment, you need a force times an eccentricity. Okay, Dave is causing this teeter-totter to spin in that direction. If I curl my fingers of my right hand in the direction Dave's causing it to spin, I can then point my thumb, and my thumb is pointing into the page, which is negative. So Dave's causing the teeter-totter to spin in the negative direction. And to be a moment, you need a force times an eccentricity. There's nothing else causing this to spin or resisting it from spinning. So let's fill in what we know about this equation. We know that Shannon is causing it to spin, or has a weight of 0.65, and her eccentricity is 0.8. We know that Dave is 0.85, and we don't know Dave's eccentricity, but we want to know what his eccentricity has to be for the sum of all of these moments to be 0. Or what does it take for this to be in static equilibrium? Where does Dave need to sit for this to be in static equilibrium? We can solve this. The eccentricity of Dave is, we can take this, bring it to the other side, and divide by Dave's weight. So we have 0.65 times 0.8 divided by 0.85. We get 0.611764 meters. Or Dave needs to move forward a tiny little bit. Dave needs to move forward, almost 8 inches, around pretty close to 200 millimeters. Not quite, but pretty darn close. So Dave needed to scooch forward a little bit so that his distance from the support was 0.612 meters away. So he needed to be closer to the fulcrum, or the center of our teeter-totter, than Shannon did because he weighs more. This is way more fun when you're sitting here, Dave. This is way more fun when you're sitting here.
Oh, really? Because you know that all your digs are landing?
Yeah.
Yeah.
Yeah, it's great.
Hey, if you want to take a break from that.
Okay, hold on. Let me stop this, guys. Okay, so that showed us what it took for Dave, what Dave had to do to stop this from rotating. Sorry, I wanted to make this smaller, not bigger. Okay. Here it is worked out a slightly different way, but you can see we get the same answer. Okay, here is a thing that is trippy. That teeter-totter, I know it's just a small image of it here, but this teeter-totter, we talked about it spinning about here because we know that's what it wants to spin about. But is the teeter-totter spinning about this point either? No. If it's not spinning here, it's not spinning here. If it's in equilibrium, it is in equilibrium everywhere. If it's...
3/4 ply, right?
Yes, 3/4 plywood. And I was assuming for one side good, or both sides good?
Yeah.
Sorry, I'm building some shelving and Dave is going to Home Depot, so he's going to buy the plywood and get it cut. So I had made a cut sheet for him. So if it's not moving anywhere or everywhere or rotating. So this is a bit of a mind trip for people. For whatever reason, this one is hard, but it's very simple. If you are not spinning about your feet, you're not spinning about your head. If you are in equilibrium, you're not spinning or moving anywhere. We can talk about summing the moments about any point we want. If we want to see what it takes for it to be in equilibrium, it has to be in equilibrium everywhere. So no matter where you sum it up, it still has to be in equilibrium. So we talked about spinning the teeter-totter about this point. What if, instead of that, we figured out what it would take or where Dave would have to sit if we imagined the teeter-totter was spinning about my bum? So instead of putting our imaginary thumbtack here, we put our imaginary thumbtack here. And remember, we want this thing not to spin. We want it to be in equilibrium. We know what it takes for this to be in equilibrium. Dave needs to be this far from the teeter-totter support. But what if we did it just as a thought exercise and imagined the thumbtack was here? What does it take for this to be in equilibrium or to not spin about this point? Which I know you're thinking, this is bananas. How could it spin about this point? It's this point that is supporting it. Well, if it is in equilibrium about this point, it's in equilibrium about any point. So the math should remain the same. So let's do this same problem, but just slightly differently. I'm going to see if I have... Okay. So I'm going to do the same thing. So Dave and Shannon. Dave moves. But spin about Shannon. So we're going to do the exact same thing, but when we talk about it, we're going to imagine that our thumbtack is right here. Okay? So let's take a look at that. Let's draw this out. We're going to see that the drawing looks the same. we have our reaction is still right here. Our y and our x are still right here. We haven't moved our support. We're just going to talk about this imaginary thought of a thumbtack, or what stops, or where we're spinning our object about. So PS and PD ES and ED. Okay, let's take a look at this. All right. First part is easy. It's the exact same. Sum of the forces in the X. We're not trying to spin it about anything, so it doesn't matter. It's just the forces in the X direction. Our X equals 0. Sum our forces in the Y direction, with upwards being positive. Well, that hasn't changed. We have minus Shannon, minus Dave, plus our Y equals 0. Our Y has to be 1.5 kilonewtons. So we need a reaction that can support 1.5 kilonewtons to stop this from sinking into the center of the Earth. But it still hasn't told us where Dave needs to sit. So let's now sum our moments about the z-axis with everything being 0 or in equilibrium, and everything spinning in that direction is positive. But let's imagine our thumbtack is here. So we're going to spin it about Shannon instead of about our reaction. So we're going to put our imaginary thumbtack here as we talk about this. So if we imagine this spinning about this point here, does Shannon cause the teeter-totter to spin about this point? Remember, you need a force and an eccentricity to cause something to spin. And I'm trying to spin it about this point. Well, if I push there, it just causes it to slide. It doesn't cause it to spin. So Shannon doesn't cause it to spin about this point. Let's take a look at this. Does Ry cause it to spin about this point? It does. Ry tries to spin it in this direction. Well, then if I take my right hand and point my thumb up, it tells us it's trying to spin it in the positive direction. So Ry is trying to spin the teeter-totter in the positive direction about Shannon's bum. Acknowledging that that's not how it's actually functioning, but let's follow through the math. We know it's not moving. We want to know what it takes to be in equilibrium. So if we put the thumbtack there, to be a moment, you need a force and an eccentricity. Ry is ES away from Shannon. Rx is passing through our thumbtack, so it's not causing it to spin. Just translate. PD, or Dave. Dave is causing it to spin about Shannon, and that is our eccentricity. Dave is causing it to spin in that direction. Use my right hand to see my thumb is pointing into the page, so he's spinning it in the negative direction. So PD, and Dave is causing it to spin this distance, or times ES plus ED. We want to know what ED is. We want to know what it takes for this to be in equilibrium. Well, look at this. We've already solved for Ry. So we've got plus 1.5 times ES, which we know is 0.8. That's been given to us since the beginning. Minus PD, which is 0.85 kilonewtons, times 0.8 plus ED, or the eccentricity of Dave. Okay, we can start to solve some stuff here. We've got 1.5 times 0.8 is 1.2 minus 0.85 times 0.8, so minus 0.68 minus 0.85 times ED. equals 0. Okay, we add this up and bring it over here and divide by 0.85. We can rearrange this, and so we get 1.2 minus 0.68 equals 0.52. Bring it over to the other side and divide by 0.85. 1.2 minus 0.68 divided by 0.85. We get ED equals 0.611764 meters. So it doesn't matter what point we pick to sum the moments about. If this is in static equilibrium, it's in static equilibrium. The distances will all be the same, the dimensions will all be the same, and the forces will all be the same. But as a thought exercise, we can pick any point to spin the object about, as long as it's in static equilibrium. If this is in static equilibrium, Dave has to be 0.61167 away from the support, no matter what imaginary point we spin this about. So people have a hard time with that, but it's a good practice to be able to do, because we're going to start not knowing what point to pick about. This one was kind of obvious because we had a teeter-totter, but we're going to be able to pick our own spots now. We want to make sure our object doesn't move up and down, slide back and forth, or spin about the z-axis. So here it is worked out again. Okay, let's start with an example. We want to figure out what the reactions of the following beam for it to be in equilibrium. We want to know what these reactions need to be for this thing to be in equilibrium. Here's where I want you to think, what is happening here? Okay, we've got small loads down here and high loads up here. What end do you think is going to have a bigger reaction? Do you think our L is going to have a higher reaction, or our R is going to have a higher reaction? Well, I think intuitively you understand that there will be more load here at RR. So let's go through and do this example. So we have a 20 meter long beam, and there's 2 meters between every force here, and they go up by a kilonewton each time. So let's draw this out here. Okay. We have a beam . All right, we have a beam here that has an unknown reaction at the left end and an unknown reaction at the right end. And we have applied loads that go all the way from 4 kilonewtons, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we've got a beam spanning between 2 supports, picking up all kinds of loads along its length. If you imagine me sitting on the table behind, or you imagine the table behind me, these are the legs of the table, and there is someone sitting every little bit along its length, and they're getting heavier and heavier as we go down it. Remember, to be a free body diagram, we need all the forces, all of the reactions, their directions, and their distances. We've been told that these were 10 spaces at 2 meters each. Or this is 20 meters long. All right, what do we think? Do we think The right end is going to have more support than the left end or the left end. Which one needs to be able to support more load? I think this end. There's a lot more weight up here. So I think RL is going to be less than RR once we do all this. Okay, so let's take a look at this process. All right. First things first, let's sum the forces in the x direction. Everything going in this direction being positive, 0 equals 0. We have nothing happening in the x direction. Okay, let's sum the forces in the y direction with everything upwards being positive. I'm a little bit cold. I'm just going to turn my heat on right now. Oh, nuts. It's already warm in here. I'm going to turn it up a little bit anyway. Okay. Let's sum all the forces in the y direction. Well, RL is pointing upwards. So we've got plus RL. And RR is also pointing upwards. And then we have minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 11, minus 12, minus 13, and minus 14 equals 0. All of these were acting downwards, so they're all negatives. All right, 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 equals 99. Bring that over to the other side. We don't know anything about RL and RR, but we know the two of them added up equals 99 kilonewtons. We don't know what their values are, but we know that the entire force pushing downwards is 99 kilonewtons. So some combination of RL and RR need to equal 99 kilonewtons. But we don't know what that is. Luckily, we have another equation that can help us determine equilibrium here. The sum of all of the moments about the z-axis also has to be 0. For this to be in equilibrium, it can't move sideways, it can't move up and down, so the sum of these has to be able to resist 99 kilonewtons, but it also can't spin in space. So we can pick some, and it doesn't matter if it's not spinning in space, it's not spinning about any point in space. So let's pick a spot to imaginarily try to spin this about to determine equilibrium that gets rid of one of our unknowns. So I am going to imagine I put a thumbtack right here, and I'm going to try to spin this object about that point. So I'm going to use RL as my thumbtack point. Okay? So RL tries to push directly through the thumbtack. It doesn't cause a moment. A moment needs a force and an eccentricity. 4 kilonewtons pushes straight down through our thumbtack. It does not cause a moment. To be a moment, you need a moment times an eccentricity. Okay, let's come over here. Thumbtack, 5 kilonewtons, causes this to spin in this direction. I'm going to curl the fingers of my right hand in the direction it tries to spin it, and then my thumb will tell us what direction it's trying to spin it. It's in the negative direction. So we have minus 5 times, and to be a moment, you need a force and an eccentricity. In fact, I'm going to write this down here because I know this gets long. So minus 5 times its eccentricity is 2. Thumbtack here, 6, tries to spin it in this direction as well. We've got minus 6 times 4. Looks like we can keep doing this. All of these are trying to spin this in the negative direction. So we've got minus 6 times 4, minus 7 times 6, minus 8 times 8, minus 9 times 10, minus 10 times 12, minus 11 times 14 minus 12 times 16 minus 13 times 18 minus 14 times 20. We have one more thing. Our thumbtack is here. Our R is trying to spin this in this direction. Okay, our R is 20 meters away as well. So we have plus RR times 20 equals 0. Because we want to figure out what it takes for this to be in equilibrium, or for the sum of all of these moments to actually be 0. Okay, we have 5 times 2 plus 6 times 4 plus 7 times 6 plus 8 times 8 plus 9 times 10 plus 10 times 12 plus 11 times 14 plus 12 times 16 plus 13 times 18 plus 14 times 20. So I've multiplied all of these negatives and then brought them over to the other side. So RR times 20 equals 2,510 divided by 20 equals, sorry, I am adding up something wrong here. I've probably plugged something into my calculator wrong here. All right, let's do that again. Let's plug this into my calculator again. All right. 5 times 2 plus 6 times 4 plus 7 times 6 plus 8 times 8 plus 9 times 10 plus 10 times 12 plus 11 times 14 plus 12 times 16 plus 13 times 18 plus 14 times 20. That's right, equals 1,210. So this is why it's always a good idea to write out what you think up here, and then we know the total has to be 99. So Rx, we can figure out, or RR equals 1,210 divided by 20, or 60.5 kilonewtons. Okay, so we now know that this end needs to be able to support 60.5 kilonewtons. Well, look at this. We have this equation here. So RL equals 99 minus RR, or 99 minus 60.5. RL, 99 minus 60.5, gives us 38.5 kilonewtons. So for this to be in equilibrium, so for this beam to be in equilibrium, the left end needs to be able to support 38.5 kilonewtons, and the right end needs to be able to support 60.5 kilonewtons. The total of that is 99 kilonewtons, which is what's trying to push down into the center of the Earth with this. So now, if you can determine the loads on a beam, you can figure out what the reactions are that support that, or what we need, what is required to stop this beam from moving. And if it's moving, we don't have a stable structure. So to be stable, we need the sum of all of these equations to be 0. So now we have a method to find reactions. And this is huge. Now all of a sudden we can start to move the loads through our building. Okay, I'm going to stop this and see how much time we have left. Okay, we have lots of opportunity to do more examples. So let's take a look at another example. Okay, let's take a look at this diving board. What are the reactions of the diving board if it's in equilibrium? Before calculating, ask yourself, what end do I think will be higher? And will it be higher by a little, or will it be higher by a lot? What end do I think? can do this. We know how to do this now. We've got 1.2 meters here, 0.4 meters here, and 1.5 kilonewtons acting downwards. So we know we have 3 equations to prove equilibrium. Okay, so diving board 1. All right, diving board 1. We have reactions here and here. And this is a reaction at the left end, and this is a reaction at the right end. We know that this is 1.2 meters, and we know that this is 0.4 meters, and we've been told that there is a force of 1.5 kilonewtons right here. Okay, let's take a look at this. If this is my teeter-totter and I have, or my diving board, and I've got 2 supports right here, and I push down on this. Whoa, that was crazy. This end tries to lift up. This stops it from sinking down into the center of the earth, but this tries to rotate. For this not to rotate, it looks like I need to hold down on this. I need to pull down on this. How will we know if things are pushing up or holding down in our reactions? So here's where I'm going to give you a tip. Always draw your unknowns in your positive direction. If you draw things in a positive direction, a negative number will mean you're wrong. And if you get a negative number, then it also means it's going in the negative direction. Okay? If I drew something in the negative direction and I got it right, that would mean it was positive, saying I was right. Okay, I know I'm confusing you right now. Let's go through an example. I know that this really needs to be an arrow, a reaction pointing down, but I just know that because I happen to intuitively understand how this one works. I need to put these here, and you know that when you jump on a diving board, this end tries to kick up. So instead of supporting something going down, instead of pushing up, it's trying to lift up, and we need to pull it down. But let's start with the same process, okay? Let's start with, we're going to do the same thing we always do. Let's sum our forces in the x direction with everything in that direction being positive. 0 equals 0. Okay, we're good. Let's now sum our forces in the y direction where everything upwards is positive, and we want to know what it takes for this to be in equilibrium. Well, we've got our left reaction going upwards, which is positive. We've got our right reaction going upwards, which is positive, and we've got 1.5 kilonewtons coming downwards. So we know that RL plus RR has to equal 1.5 kilonewtons. We don't know how that breaks up. We've guessed that this one should actually be pointing in the opposite direction, or pointing downwards in the negative direction. Let's try summing the moments about the z-axis, and we want to know what it takes to be in equilibrium, and everything spinning in this direction is positive. And I am going to pick right here as my thumbtack. You could pick right here. You could even pick right here. It's up to you. I'm lazy. I'm going to always pick this point for this type of exercise. It's just probably going to make my life easy to have a pattern that I don't have to think about too much. I'm going to pick this node right here to imagine I'm trying to spin this diving board about. Okay? So I'm going to put my imaginary thumbtack right here. RL tries to push directly through the thumbtack. To be a moment, you need a force and an eccentricity. That doesn't have an eccentricity from that point right there. Therefore, it's not causing it to spin. RR is causing this to spin in this direction. I can curve the fingers of my right hand in the direction it's trying to get it to spin, point my thumb up, that's telling me it is spinning it in the positive direction. So plus RR times, remember to be a moment, it needs a force, times an eccentricity. Our eccentricity is 1.2 meters. Put our thumbtack right here. We've got our force pushing down, trying to spin this in this direction. Take my right hand, curl my fingers in the direction it's trying to spin it, and then my thumb can tell me that that's spinning it in the negative direction because my thumb is pointing in the negative z-axis. So minus 1.5 times its eccentricity. This distance is 1.2 plus 0.4 or 1.6. I can rearrange this and it looks like I can find RR. 1.6 times 1.5 and you bring it over here and divide by 1.2. 1.5 times 1.6 divided by 1.2 equals 2. R equals 2 kilonewtons. Well, that's crazy. We only have 1.5 kilonewtons pushing downwards, and we have 2 kilonewtons pushing up here. So that means we must have something here holding it down. We've already solved this equation here. Let's plug our RR in. RL plus 2 equals 1.5. RL equals minus 0.5 kilonewtons. So RL needs to be an arrow pointing in the other direction. The negative value tells us we drew our arrow wrong. We didn't know what way to draw our arrow, so we guessed the positive direction. And I'm going to be lazy and always do that. I'm going to suggest you do the same. That means a negative value telling us we're wrong also happens to always point in the negative direction. If we had done this drawing our arrows downward, our L would have come out positive and our R would have come out negative, meaning we had drawn our R in the wrong way and it should really be upwards. That can start to get confusing. So I will strongly recommend always draw your reactions in the positive directions, and that way a negative answer tells us it's actually going in the negative direction, okay? Or that we've drawn our arrow wrong. You can do one of two things here if you ever want to. Both of these two things are true. So I'm just going to draw a mini version of this. So that's kilonewtons, and that's kilonewtons, and that's meters, and that's meters. You can continue to draw the arrow upwards and say that it's minus 0.5, because that really means it's going in the negative direction. Or you can draw it as 1.5 kilonewtons, 2.0 kilonewtons, and 0.5 kilonewtons. And that's 1.2 meters, and that's 0.4 meters. These two things are the same. The negative tells me that arrow is pointing downwards. Here, the arrow is visually pointing downwards, so I wouldn't include the negative. Okay? We need to be able to show that that is actually going downwards. Drawing it up with a negative means it's going downwards. Drawing it downwards with a positive number means it's going downwards. What happens if we shorten the back span of that diving board? So we have the same person jumping at the front of the diving board, or standing at the front of the diving board, but we've shortened the back span. This is our cantilever, and this is our back span. What do we think is going to happen here? So let's do diving board 2. So we had our support right here. We went out 400 and 400. Okay, so we have 1.5 kilonewtons right here. We have an unknown support here and an unknown support here. So let's call them RL and RR. And we know what the dimensions of this diving board are. It's 0.4 meters and 0.4 meters. Okay, so the force is the same. The cantilever is the same. The only thing different is the backspan. What does that do to our reactions? Okay, sum the forces in the x direction, so everything is 0, and that way is positive. 0 equals 0. Okay, we've got our reactions in the x direction solved. We don't have any. We have no forces and we have no reactions. All right, let's sum the forces in the y direction, where everything upwards is 0. We have RL plus RR minus 1.5. Upwards, upwards, downwards. All needs to equal 0. So RL plus RR equals 1.5 kilonewtons. So again, this is the exact same. This equation here looks identical. Let's take a look at our moments. Let's sum the moments about the z-axis so that the system is in equilibrium and everything spinning in that direction is positive. Let's pick this node as our thumbtack. Remember, I'm lazy. I usually pick the first reaction on this end to be my thumbtack spot. I could pick wherever I wanted, but I'm going to pick this point right here. So here's where my thumbtack is going to go. Okay, so I'm going to spin it about RL. Okay, if we're spinning it about RL, I'm putting my thumbtack right here. RR, well, RL goes right through it. RL doesn't try to make it spin, just slide. RR tries to make it spin in that direction. If I curl the fingers of my right hand in the direction it's trying to spin, when I point my thumb, it'll tell me if that moment is positive or negative. My thumb's coming out of the page, so it's positive. So RR is trying to spin in the positive direction, and to be a moment, you need a force times an eccentricity, and its eccentricity is 0.4 meters. Put my thumbtack right here. 1.5 kilonewtons tries to make it spin in that direction. Curl the fingers of my right hand in the direction it's trying to spin, and then when I point my thumb, it'll tell me if it's positive or negative. My thumb's pointing downward, so it is trying to spin in the negative direction. 1.5, to be a moment, you need to be an eccentricity, or a force times an eccentricity. We have 1.5 times, and we're spinning it about this point, so its eccentricity from that point is 0.8 meters. And we want to know what it takes for this system to be in equilibrium. So we can rearrange this and find RR. So negative 1.5 times 0.8, bring it over to the other side and make it positive, and then divide by 0.4. So 1.5 times 0.8 divided by 0.4 equals 3 kilonewtons. Whoa. On this one, our right reaction was 2 kilonewtons, and now our right reaction is 3 kilonewtons. That's interesting. Let's see what it does to our left end reaction. Remember, the sum of this up and down has to be 0. If we're now pushing up with a higher force at this spot right here, we must be pulling down with a bigger force here. So we can plug into this. RL equal or plus 3 equals 1.5. We can rearrange for RL, and we get minus 3 plus 1.5, or minus, equals minus 1.5 kilonewtons. So here we had minus 1.5 and 2. Now we're going to have, with our shorter version of this, we're pushing up with 3 and we're pulling down with minus 1.5. So shortening the backspan increased our reaction forces. Even though the load on the system didn't change, this tendency to want to spin, it increased our forces right here. So that's kind of interesting. It seems like we've got some cool tricks now to be able to solve for some of these reactions. Okay, so here are all of those worked out. So here are your takeaway tips. Okay, let me turn this up here so that you can see me. All right. Okay. So, moment, force times eccentricity. A force not acting through the centroid can be rewritten as a force through the centroid with a moment. So it's sliding and spinning. There are 6 degrees of freedom, 3 of movement and 3 of rotation. We often work in a 2D world, and we could simplify it, but a 3D world, which is where we live, has 6 degrees of freedom. We need to restrain structures in all 6 directions, or all 6 degrees of freedom to have equilibrium. We want equilibrium because that means it's static, and we don't want our buildings flying off into space. That would be a really poor building if it flew off into space. We can simplify it by looking at a 2D plane, so 2 of movement and 1 of rotation. We know if it's in equilibrium, the sum of all of our forces must be 0. And so we can do that up and down, or side to side, or spinning about a point. And if it's in equilibrium, it doesn't matter what point we pick to sum it about, it's in equilibrium. If it's not spinning about one point, it's not spinning about any point. So if there's no spinning, it doesn't matter what point we pick. And that is true for our static objects. If it's not static, none of that makes any sense. But if it's in equilibrium, it doesn't matter what point we pick to spin it about, it's in equilibrium. So with that, we now have 3 handy equations to solve for our reactions, or the reactions we have to have so that our object is in static equilibrium. So 3 equations will let us know what it takes to support our object. And then we can go about designing that thing, designing that support. But it seems like there's more. We had that long beam, for example, the one that had all of the forces getting higher in it. Most of the force went to one end and some of the force went to the other. What happens in between? What's going on inside the beam? That seems like the thing we'd want to talk about next. We know what happens to support it so that it's not moving around. So it looks like we've got a stable, static structure, and we know now we can design what it takes to support that structure. But we still haven't designed the object itself. Something's happening inside there to get all of those loads out to the reaction points. And so next week, we need to figure out what's happening inside that object. What are the internal forces inside this object? And that one's a really fun one. We're going to start talking about method of sections next week. But really, it's just using the same 3 equations. It's going to be really easy once you get your head around the fact that we're talking about something that's static. Okay, so I'll see you guys next week.